All right, everybody, we're going to pick up where we left off and we're talking about enzymes. And enzymes are really important in our bodies. They are also called a catalyst, and basically they speed up chemical reactions, which is really, really important in our bodies, especially when we digest things, when we need any chemical reaction to happen. Really, we need this an enzyme to come in and take care of the work or increase the amount of work we can get done. So the key thing here, one of the key things from this slide is just that they are a protein molecule. That's really important that we know what that is in our molecules of life, that it falls into the protein category. And they catalyze, which means speed up chemical reactions. So there will be a couple other videos linked up for you of show how these work, some animations that are there. But basically in a picture form here, what happens is we have substrates that come in, they link into the enzyme. They are specific to the enzyme that they will fit with. That's often called a lock and key. So if you think about having a key that fits into a specific lock and is able to unlock that door or that object, whatever it is, it's very specific. You could have one key to one lock, and that's the only one it fits in. And that's what happens with enzymes. Lock and key. They fit with this specific substrate. And what they'll do, for instance, in this case, we have a large molecule that comes in and fits into this enzyme. And through the reaction process, it will cause the substrate to split, in this case, into two products. And so this would kind of be like digestion. You take in a large macromolecule, it fits into the enzyme causes that large macromolecule to break up into maybe monomers or into smaller parts. It can go the other way though too. So you could have two substrates that come in to the enzyme, and then the enzyme forces them together or bonds them together and then releases one large product. Enzymes will get reused over and over and over. We'll talk about on another slide here that they work in like ideal conditions. So there's certain conditions that each enzyme will work in, but they can continue to be used after they've been used once. So how enzymes work, the reactants or the substrates join in what's called the active site of an enzyme. And if you're using the notes packet, you'll see a picture that you have been given already in the notes packet that kind of show this. So that active site is like the lock. It is a specific shape for a specific substrate. And then the enzyme will form the products, either link up individual monomers maybe, or it will break apart a large macromolecule. It will release the products, and then the enzyme returns to its original shape to be reused. Enzymes are affected by changes in pH, which is like the acidity level, and also by temperature. There are other things too, but you'll see in the lab we're going to do in class that we're going to focus on pH and temperature. Each enzyme is going to work best in a specific pH and temperature range for that particular enzyme. This is related to where it is in the body. And so an example here is pepsin is found in the stomach, and it works best at a pH of 1 to 2. That's your pH level that's in your stomach in order to digest foods. So this particular enzyme will work best at that pH level. And you can see this in some graphs. We'll talk about these a little bit in class, and we'll be working with these as we do labs. But in this case, we have 3 different enzymes, and each of them has a different pH range that it works best in. So this particular enzyme, I don't know, we could say it's around a 2, the one in blue here. And we're kind of I'm basing that off of our graph here that shows a pH of 7 here in the middle. And so if this one in blue reaches, if for whatever reason in the body, it is a pH of 7 in the conditions for this blue one, it'll barely work. It's not going to work very efficiently. However, this one in orange that's represented in orange here is going to work really well at that pH level of 7. And then let's say this one's around, I don't know, a 10 or 11. This green one is going to work best in that pH range. Now, temperature, you can see here, this particular enzyme is going to work best around 37 degrees Celsius. And so if you take a look at this for humans, this optimum temperature range for this enzyme is there. If it goes higher than that temperature, let's say you have a fever, then the enzyme is going to what's called denature. And basically that lock or that active site is going to change shape, and it's not going to be able to accept the enzymes in. So at some point, it's going to reach a point where it's not able to accept that enzyme or that substrate at all. So it's like the lock not going, or the key not going in the lock at all for some reason, maybe like if you think about a real lock on a door, like it melts or something. The temperature is too hot and it melts a little bit, and that lock or that key won't go in. It'll also at a lower temperature also cause problems for the enzyme. Now, just to give you some idea of things in the body that ways things kind of go wrong in the body, diseases caused by a lack of an enzyme. Fetal ketonuria is an example. You might have heard of this. It's called PKU. Some food labels will show fetal ketonuria on the food label so that people who have PKU know not to eat that particular food. It results in death due to the absence of specific enzyme. Now, we as a very, I'd say, medically advanced society at this point, we don't see death from this very often because this is tested for in infants. And so then somebody who has PKU would know not to eat foods that have that particular amino acid in there. Tay-Sachs disease, it results in childhood death caused by a lack of an enzyme as well. So enzymes are very, very important. Now, one that's not as severe is lactose intolerance. And what happens in lactose intolerance is you either don't have at all or you have very little enzyme called lactase. And lactase helps to break down the sugar lactose, which is found in milk and milk products. So if you don't have that enzyme, but you drink milk, you're going to feel really crampy. It's going to be uncomfortable. It doesn't lead to death, but it's going to be very uncomfortable. So you can actually take in a lactase product, and that will help you digest milk products if you really want ice cream or something like that. However, in our food products we have now, you can buy lactose-free ice cream and things like that. So that's just to give you 3 examples of why enzymes are important. And then the last thing here is the energy graph. So to show what enzymes actually do through energy, and you might have talked about this in physical science, we have reactants here and we have products here. That's a chemical reaction. In order for this chemical reaction to occur, we need to reach a point called activation energy, and that's the total amount of energy needed for that reaction to occur. If you don't reach that energy, let's say you only reach here in the graph, then that reaction is not going to take place. So what we have in our body is an enzyme. So this enzyme, when it's added, will cause that activation energy to be lowered. And once we lower the activation energy, we can make that reaction happen faster. So we can go through the chemical reaction much faster. And we still reach the same products, but we just do it in a faster way. So a couple random interesting facts. Substrates can be transformed to usable products at the rate of 10 times per second. And it's estimated that 75,000 enzymes are in the human body at any one time. So that's kind of a quick overview of enzymes. We will be doing a couple labs in class, including one virtual lab, to help us kind of identify how enzymes work and what range of temperature and pH they will work in.